In this video, we will be learning how to do multi-step conversions between moles, particles, and mass to complete our learning objective for how to do all this interconversion between those units. So for instance, we have learned about using molar mass as a conversion factor. We have learned about using Avogadro's number as a conversion factor. And so in this problem, we're trying to go from a mass into counts. The practice problem reads, oh gosh, that has a grammatical error too. So, how many H2O molecules are in 25.64 grams? Making a note to myself about the grammar. Okay, so we are given grams of H2O. I'll go ahead and write out 25.64 grams of H2O, and we are asked to find how many molecules of H2O that is. And so for my conversion factors, I know that molar mass will help me get from grams to moles. But then I need to go from moles to counts. And so to go from moles to counts, I will need Avogadro's number. So I'm going to need both of these conversion factors. And they are joined by moles. So I need to go from 25.64 grams of H2O, and I can't go straight to counts. I'm going to have to stop over in moles of things. And so I have to go from grams to moles using the molar mass. And then I will go from moles into counts. And so that will give me my number of molecules. A lot of times students try to shortcut by combining terms, and that just leads to some weird setups that end up being wrong. So just try to isolate, like, this is my molar mass, this is Avogadro's number, and don't try to merge things together. Just keep them nice and separate. So we need the molar mass of H2O. So if you know the chemical formula, you might be able to look it up. So the molar mass of H2O is 18.015. And so then we need Avogadro's number, which is 6.022 times 10 to the 23rd power. If we didn't know that molar mass, we could also calculate it from the periodic table by adding up the mass of one oxygen and two hydrogens and ending up with that value. Now that I got my setup and I can see that my units work out, my grams cancel, and I'll end up with molecules of H2O. We do need to get in the habit of actually labeling each thing, and that will become even more important in the next few slides. But we can go ahead and type this in to our calculator, matching the format as best as possible, so that we can make sure that we are communicating with our calculator exactly what is on our paper. So I'm going to use my multi-line fraction tool to make sure that I am communicating with my calculator what's in the numerator, what's in the denominator, so that I can end up with an actual value. That is not proper scientific notation. We are only allowed one number in front of the decimal point. And so I will write my number as, I need 4 sig figs. So that's 1, 2, 3, 4. So that's 8.57. That's 3 sig figs. I need 4 sig figs. 1, 2, 3, 4. And so I'm running out of room. I'm just going to write the already rounded value. Okay. And then we'll double check what has been typed underneath. You can see that nice little diagram showing how moles connects the two. And that is the same type of number I got before. I just need to trim off a digit. So slide 24 also has a typo in the answer. I have an extra 1 underneath there. Gotta clean that up. All right, here's a practice problem for you. Go ahead and pause the video to try to work it out. It says, what would be the mass in kilograms of 8.58 times 10 to the 25th power formula units of iron 3 oxide? Pause the video to work that out and unpause the video when you are ready to continue. Okay, let's go over this. So I have iron 3 oxide by name. I have to come up with the chemical formula, most likely, because it is asking about mass, and so I'm going to have to probably use molar mass in this. So iron 3 stands for Fe3+, and oxygen has a common ion charge of 2-. And so doing the crisscross to get subscripts, that's Fe2O3 as my chemical formula. So I am given 8.58 times 10 to the 25th power formula units of Fe2O3. That's a count. And I am being asked to find kilograms of Fe2O3. So this is a mass. And so that means I'm going to have to go from counts to moles to mass. And so my map will lead me from counts to moles to mass using molar mass and Avogadro's number. So I'm going to have to start with my 8.58 times 10 to the 25th power formula units of Fe2O3. I'm going to have to cancel out my formula units of Fe2O3 and get into moles of Fe2O3. This is Avogadro's number. And then I'm going to have to use my molar mass. So I will calculate my molar mass, and so I know that that is 2 iron, so that's 2 times, let me clear, 2 times 55.85 plus 3 oxygens. That matches what I have in my head. And so I know I have to cancel out moles, so moles has to be in the denominator. I have to get to grams. This number is attached to the grams. Now I have this all set up, and so now I'm ready to type the full thing into my calculator. And so that is 8.58 times, well, hit clear, I'm not typing into the right spot. 8.5, that's not 8.5, 8.58 times 10 to the 25th power times 1. And then I'm going to type this in for those of you who do not have multi-line displays. So I am typing that into the denominator, but making sure to use parentheses around it. And then if you'd like to divide by 1 just for fun, you can. And oh, it said kilograms, didn't it? We didn't do the kilograms yet. We got to erase this little equal sign. And so I have to go from grams into kilograms. And so 1 kilogram is 10 to the 3rd power, which is 1,000. And so I'm going to do, I just did that. And so now I got to continue my calculation times 1 divided by 10 to the 3rd power. And so that will be 22.753 kilograms. I need 3 sig figs. It won't let me write the G right here. So that's 1, 2, 3 sig figs, and so that's 22.7. That 5, though, is going to round that up into an 8, so that my last digit is even. So it's 22.8 kilograms. Good, matches what's underneath. Okay. So in this part of the video, we introduced that we can use subscripts as additional conversion factors in our math. And so this analogy includes that one spider has 8 legs. And so if we wanted to know how many legs were in a whole case of spiders, we could use that as a conversion factor to take the number of spiders and figure out how many legs that is. Similarly, chairs only have 4 legs. And then one water molecule has 2 hydrogen atoms. And so if we wanted to know how many hydrogen atoms were in a given set of water molecules, we can use the subscripts in that chemical formula to figure out how many hydrogen atoms that is. So the subscripts in the chemical formula can either relate the number of molecules to the number of atoms at that small scale of individual items, or we could scale that up. And so instead of talking about one individual molecule, we could talk about a whole mole of that molecule. And so one molecule of H2O has 2 H atoms, but 1 mole of water molecules contains 2 moles of hydrogen atoms and 1 mole of oxygen atoms. So those subscripts can either relate things on the molecule atom scale or at the mole scale. Here's an example of how that would work. This problem reads, what mass in grams of calcium carbonate contains 7.512 times 10 to the 22nd power oxygen atoms? And so I am given 7.5, that's messy, I'm just going to rewrite that. 512 times 10 to the 22nd power O atoms, that's a count. And I'm asked to find mass in grams of calcium carbonate. And so I can see here that I am asked about different things. whenever I'm asked about different things, I have to think about what kind of mole ratio do I know that can relate those two things together. And so my conversion factors are going to include the subscripts that tell me that for every one of this compound, so 1 mole of CaCO3 will have 3 mole of O atoms. And then we will have, we're going from counts to mass. And so in addition to the subscripts, I'm going to need to go from counts to moles to mass. And so I'm going to have to stop over in moles first. I go from counts to moles using Avogadro's number, which is abbreviated Na. And then I go from moles into mass using molar mass. So I'm going to need 3 different conversion factors for this particular problem to get all my changes done. So 7.512 times 10 to the 22nd power oxygen atoms. And I could either do subscripts first, or I could wait until after I have moles. So I'm actually going to go into moles first since I wrote these in moles for you. And so I'm going to use Avogadro's number first. And so I'll get into moles of O. And so I'll cancel out my 6.022 times 10 to the 23rd power counts of oxygen atoms and just get into moles of oxygen atoms. Then I will use my subscripts in the chemical formula to cancel out my moles of O and end up with moles of the whole compound. You see how the labels are really important here? And so for every one of the whole compound, I have 3 oxygens. Now I need the molar mass. And so I could calculate the molar mass, or this app allows me to search for it. Let's see how this works. Okay, calcium carbonate. And so that is 100.088 grams per 1 mole. And so now I can go back and I can type this all into my calculator. And so that is 7.512 times 10 to the 22nd power times, I like the multi-line fraction, so I'm going to do that. 6.022 times 10 to the 23rd power. And then I need a 1 over 3. And then I need a 100.0088 over 1. And so I highly encourage that you type it all into your calculator as one calculation. That way you avoid any rounding errors or re-entry errors from hitting equals and typing things in multiple times. I don't have room on this line, so I'm going to write my answer up higher. I need 4 sig figs. And so that would be 4.16. Well, I'm just going to write out more digits than that for now. 1, 2, 3, 4. I'm going to have to round up because the 7 is more than 5. And so that becomes 4.162 grams of calcium carbonate. So 4.612 grams of calcium carbonate contains that many oxygen atoms. And it looks like that's missing some sig figs. So slide 7, need to fix sig figs on that one. Okay, here is a practice problem for you. Go ahead and pause the video and try to work out on your own how many atoms of fluorine are in 1.65 moles of SF6. Unpause the video when you are ready to continue. Okay, let's do this. So we are given 1.65 moles of SF6, and we are asked to find counts of atoms of fluorine. And so we can see that we have two changes going on. We have a change in unit from moles to atoms, and so that change is going to require Avogadro's number. We also have a change in substance, and so that's going to require some kind of mole relationship or count relationship. And so all we know right now is subscripts that will tell us how many fluorines there are for every sulfur. So I need both of those as conversion factors. So now I know I'm starting with my 1.65 moles of SF6, and I'm asked to find, I'm going to use subscripts first. I could use either one really, but I like to think of subscripts in moles, and so I'm going to use the subscripts first. But you can do the subscripts afterwards, and it would just tell you how many atoms there are for every one molecule. Actually, I'll do that because I think the typed math underneath uses that as moles. So anyway, no, not down there. I need to cancel out moles. I need to cancel out moles of SF6, and I'll get into molecules of SF6. And so that will be 6.022 times 10 to the 23rd power for every 1 mole. Then my subscripts, I can cancel out for every 1 molecule of SF6, there are 6 F atoms. And so my molecules of SF6 cancel out, my moles of SF6 cancel out, and then I'll be left with fluorine atoms. So I can type that all into my calculator. 1.65 times 6.022 times 10 to the 23rd power times 1 times 6 over 1. I like the pretty multi-line fraction. 6 over 1. That's not in scientific notation. Let me get the scientific notation from my calculator. So that's 5.96178 times 10 to the 24th power fluorine atoms. I need 1, 2, 3 sig figs. 1, 2, 3 sig figs. So I will report my answer as 5.96. So we'll round down because of the 1. But I do have to remember the times 10 to the 24th power because there's not just 5.96 atoms, there's this many atoms. Okay, let's double check the typed math underneath. And you can see here I did use the subscripts in mole unit, but other than that, it does look the same answer was obtained in both ways. And so I believe that is the end of this video. Yep. See you in the next video when we learn about mass percent composition.